Let us discuss today the quiz paper that we had recently, and then we will go on and see where this takes us, and as I said last time, we will switch to a different topic right after this. So first the quiz. First we had a number of statements which were supposed to be marked true or false, and here they go. Any map of the unit interval that is non-invertible leads to dynamics that is chaotic. True or false? False, definitely false, because the non-invertibility is not enough, you need much more than that in order to have chaos. We have numerous examples of maps which are not invertible but which are not chaotic at all. Give me an example, a non-invertible map that does not lead to chaos, one dimensional map. Yeah, the logistic map at parameter value less than mu infinity, for example at the value of mu like 3.1 or something like that, that is not chaotic definitely. There is some stable, some period cycle which is the attractor, so it is not chaotic, it is not invertible, it goes up and comes down, it is like a parabola, so that is certainly not true. The Lyapunov exponent of the logistic map xn plus 1 is mu times xn, so xn plus 1 equal to mu times xn 1 minus xn at mu equal to mu infinity equal to 0.566 etc. This is the end of the period 2 cascade of period doubling cascade of bifurcations. This at this value 3.566 etc. So the statement is that the Lyapunov exponent at this value of mu is equal to log 2, it is false, it is 0 because it is the onset of chaos. A little bit beyond this mu infinity you have chaos as signified by a positive Lyapunov exponent. In the logistic map this becomes 2, the Lyapunov exponent reaches log 2 only when mu hits 4 and the map leads to fully developed chaos, till then it is less than log 2. For any chaotic attractor, the generalized dimension d0 is equal to the dimensionality of the phase space itself. I repeat, for any chaotic attractor, the generalized dimension d0 is equal to the dimensionality of the phase space itself. For the maps we looked at fully developed chaos in one dimension, the attractor was the unit interval itself except for sets of measure 0, and then this statement was true. But that is not true in higher dimensions certainly. Whenever you have chaos in a dissipative system, in general there is shrinkage of volume and the system sits on some attractor whose dimensionality is less than that of the dimensionality of the system itself, definitely. Even in the case of the logistic map, it is clear that the dimensionality of an attractor could be a fractal dimension between 0 and 1 even though the phase space is one dimensional. So this is a false statement, not necessarily true. Okay. If the Lyapunov exponent of a one dimensional map is positive, we may conclude that the dynamics is chaotic for all initial conditions. False, because we know that there are initial conditions which lie on periodic orbits, unstable periodic orbits, and then this is not true. That set of initial conditions may have 0 measure or may not, but you certainly cannot conclude that if the Lyapunov, just because there is chaos, the Lyapunov exponent is positive, we can't conclude that the dynamics is chaotic for all initial conditions, not true. Okay. Stability analysis using a Lyapunov function enables us to decide on the stability of a critical point even in cases where linearization in the vicinity of the critical point is invalid. This is true, this is one of the great advantages of Lyapunov's direct method. Now once you have a proper Lyapunov function, you can make definite statements about the stability or asymptotic stability or instability without having to do linear analysis. So that is the great advantage of a Lyapunov function. The logistic map, the same map, undergoes a bifurcation at mu equal to 3, a Hopf bifurcation at mu equal to 3. It undergoes a flip bifurcation from a period 1 fixed point to a period 2 cycle. The period 1 cycle, the fixed point becomes unstable, the fixed point at 1 minus 1 over mu becomes unstable and it bifurcates to a period 2 cycle which is stable for some range of mu thereafter, and that is a flip bifurcation, it is not even a pitchfork bifurcation, period doubling bifurcation. It is certainly not a Hopf bifurcation, this system does not have any limit cycle at all. A Hopf bifurcation cannot occur in a Hamiltonian system, it leads a limit cycle which happens only in dissipative systems, not in a conservative system, and therefore the statement is true. The origin, so the next question was the origin x equal to 0, y equal to 0 is a global attractor for the system given by x dot is y and y dot is x minus x cubed minus y. This statement is false. What sort of system is this? What kind of system is this? Can we think of a physical system which has this set of equations? Any potential, yeah, there is damping. It is clear that if you regard this as the position in one dimension, this is the velocity with appropriate units, and then this is a damping proportional to the velocity in magnitude. So it is a damped system provided this portion can be identified as a force arising due to some potential. Now what would that potential be? So if I plot x here versus v of x, v of x would be minus the integral of this, since the force is minus the derivative of the potential is minus the integral of the force. So what would this give you? This leads to a potential v of x which in these units is equal to what? Plus or minus x squared over 2? Minus x squared over 2. So it is minus x squared over 2 plus x4 over 4 in this fashion, right? And then what? What sort of potential is this? It is a double well potential, so definitely its potential looks like this fashion, and the origin is a point of equilibrium, it is a critical point, but it is actually a saddle point in this case, and you end up with 2 in the undamped case, and then you end up here with 2 attractors. They are actual attractors here because this is a damped system, they are not centers. If the damping were absent, this would be a center, these 2 points would be centers and that would be a saddle point, but now you actually have 2 critical points here which are asymptotically stable. What sort of critical points are they? There is damping present in the system, yeah, these things would actually be asymptotically stable spiral points, and then in between you have an unstable equilibrium point here. So this is not a global attractor, nor is this, nor is that, there are actually 2 attractors in the system, and depending on what your initial conditions are you would fall into one or the other. There will be 2 basins of attraction for the 2 attractors. So this is just the Duffing oscillator, the double well potential with unforced Duffing oscillator with the linear damping, it is the Duffing problem. The winding number of the singularity at the origin of a planar vector field has been given to you, and you are asked to show that, asked whether the winding number is equal to minus 2 or not. Let us check. Let us check. So f of x comma y is equal to x squared minus y squared over x squared plus y squared the whole squared minus 2xy over x squared plus y squared the whole squared. It is a planar vector field which is singular at the origin, as you can see, probably blows up at the origin because of these denominators. Okay. Now what do these things suggest? I mean this x and y components of this vector field suggests that they are the real and imaginary parts of some function of a complex variable z. What would that be? Z bar squared. So these things are, this thing here is 1 over z squared. That is the vector field. So if I write this as x plus iy whole squared, I get an x minus iy whole squared on top, and below it's x squared plus y squared, the whole squared. So that is precisely the real and imaginary parts of this. So you could write this in complex notation as z dot. If it is a dynamical system, you would write this as z dot equal to z to the minus 2, and the vector field is z to the that of minus 2. So what is the winding number? I go around once around the origin in the z plane, and what is the amount by which the argument of this vector field increases or decreases? Well, if z goes to z e to the 2 pi I, goes around once, then how much does that increase by? Minus 4 pi I, right? So that is what the argument changes by. So the argument changes by minus 4 pi, and as a multiple of 2 pi, it's minus 2 times 2 pi, and therefore the winding number is equal to minus 2. Yes.
This is, if you put y is equal to minus y.
Yes.
Except for the reduction in the field due to the x square plus y square term,
right,
it is exactly the same field. Right?
The dipole field would correspond to z squared plus 2.
No, my argument
Yeah.
is this.
Yeah.
This is equivalent to the dipole field in the sense that if you replace y by minus y,
Yeah.
and then it is equivalent to the dipole field except for the factor below.
Yes, but that is all important, that is absolutely all important. You see, whatever happens in the dipole field at the origin, suppose I put z is equal to 1 over u for example, then clearly whatever happens in the origin in z happens at infinity in u, and vice versa. So because it is 1 over z squared, what you should really do is to make a change of variables to 1 over z, in which case this field is just u squared, the winding number is plus 2, but now you map back to 1 over u, and then it changes sign, because whatever goes around counterclockwise once in this direction, viewed from the point of view the point at infinity, it is going around in the opposite direction, right. If I imagine the point at infinity to be the north pole and the point or the origin to be the south pole in stereographic projection, and I go around once around the south pole in a specific direction, viewed from the north pole it is going to be in the opposite direction. So that is precisely what is happening. This minus 2 is what appears here, and therefore the winding number is minus 2 rather than plus 2. Okay. So that was just a small change on the usual dipole field. Okay. This field is singular at the origin, it does not vanish at the origin, it blows up at the origin, becomes infinite at the origin. The next question was, the damped unforced Duffing oscillator cannot have any limit cycles. True or false? It is true. We proved this by the Poincaré-Bendixson, the Bendixson criterion. We showed that in this case, in the damped unforced Duffing oscillator, whose equation we wrote down a little while ago, you can't have any limit cycles at all, simply because the vector field's divergence has a specific sign. So we saw that as soon as that is the case, you can't have any limit cycles. We use Green's theorem in the plane to establish this fact, the Bendixson criterion. Okay. Then the next question was, consider the map xn plus 1 is xn times 3 minus 4 xn squared. So let me write this map down. Xn plus 1 equal to xn into 3 minus 4 xn squared, and x naught is an element of minus 1 1, and the statement is this map has a stable period 3 cycle. Is that true or false? It is false, because we can see this immediately. What does this map reduce to? Yeah, it just reduces to like the Bernoulli shift except in ternary, the slope 3, because we can see that directly. Let us plot this map. let us plot it here. This is minus 1 1, this is minus 1 and 1. It is an onto map as you can see, and when xn is equal to 0, xn plus 1 is also 0. When xn is plus 1, then it is 3 minus 4, it is minus 1, and vice versa. So this map does something like this. It is a cubic map, does this. It does have fixed points. There is a fixed point here. The slope at the origin is 3, that is bigger than 1, so it is immediately unstable, that is clear, and it is an easy matter to see that these slopes are also greater than 1 in magnitude, and therefore all the fixed points are unstable. If you iterated this map, what would happen? If I took f2 and f3 and so on and iterates of this map, what would happen? They just go up and down a few more times, but the slope would again be much greater than 1, get increase as the number of iterations increases. So it is clear that this map has no period cycles at all, no stable periodic orbits at all. So not only are the fixed points, but all the higher periods periodic orbits of this map are completely unstable, it is fully chaotic. So you should not imagine that these 3 points form a period 3 cycle to start with, they are just fixed points of this map, and it has no fixed points which are no periodic points which are stable. Now to see that this map is actually a shift of some kind is not very difficult. All you have to imagine is to put xn is equal to some trigonometric function, sine or cosine or whatever it is. So you put sine theta n, and then you discover that you have a formula for sine of 3 theta as sine theta in terms of sine theta here, and it says that 3 theta n plus 1 is 3 times theta n minus 1 theta n, and therefore theta n is 3 to the power n times 3 theta naught, and that is like the Bernoulli shift in this theta variable. So since we have it between minus 1 and 1, the obvious thing to do is to make it like this. So let me call it yn, and then yn runs from minus 1 to 1. So with this change of variable, this is immediately solved. This map is immediately solved in closed form. It is the analog for the cubic map of what the logistic map would have been at mu equal to 4, where also we made a trigonometric change of variables and we got the Bernoulli shift, the doubling map. Okay. The next question was, let x of t be a dichotomous Markov process in which x jumps randomly between two values x1 and x2 with mean residence times tau 1 and tau 2 in the two states. And we said let the mean be 0, that is not necessary, but let the mean value be 0. And the statement is the autocorrelation function of the process is a decaying exponential function of t. This is a true statement for a dichotomous Markov process. No matter what the levels are and no matter what the rates of transition are, the autocorrelation function is an exponential function. The reason I said let the mean be 0 was because I did not want x minus the mean value at x of 0 minus the mean value times x of t minus the mean value. That is the general autocorrelation function, and I wanted to get rid of that mean. So I defined the mean to be 0 here. So in this case you have a process which goes up and down in this fashion between two values, and we saw that if the value here is x1 and the value here is x2 and we arrange the rate so that the mean is 0 somewhere there, and if this rate is lambda 1 and this rate of transition is lambda 2, then this autocorrelation function x of 0 x of t, this goes like the mean square value whatever it is x squared multiplied by e to the minus 2 lambda t, and 2 lambda is lambda 1 plus lambda 2. That is a general statement, not very hard to derive for a dichotomous process. So it is an example of a very simple model of a Markov process which is exponentially correlated, occurs in numerous applications. and the characteristic time is 2 lambda inverse, which is the sum of the inverse of the sum of the two rates. Okay. Now that is worth noting. If the mean time of stay in this state is tau 2, which is lambda 2 inverse, and this is tau 1, which is lambda 1 inverse, the mean times are tau 1 and tau 2, then one should not come to the conclusion that it's the correlation time is tau 1 plus tau 2, not true, it is in fact this. So this guy here 2 lambda inverse is the inverse of this, which could be written in terms of tau 1 and tau 2, and what does the correlation time come out to be in terms of those two? Tau 1 tau 2 over tau 1 plus tau 2. Okay. So much for that. Then the next question, give a set of numbers between 0 and 1. So let S be the set of numbers such that the decimal expansion of any x element of S is of the form x equal to 0.a1, a2, etc. So we are starting with all the numbers between 0 and 1. This is the S is an element of 0 1, and then we have the set of numbers is of the form x is 0.a1, a2, a3 dot dot dot, each ai is odd, namely they can't have the sorry, in other words the digits, each of the digits is even, can't have the values, each ai is even, does not matter, but equal to 0, 2, 4, 6 or 8. And you are asked to calculate the fractal dimension, the capacity dimension or the box counting dimension of the set S. Yeah. So what you do is simply say, you take the interval between 0 and 1, break it up into 10 equal parts, so 1, 2, 3, 4, 5, 6, 7, 9 and 10, so 0 to 1, and this is 0.1, 0.2 here, etc., right up to 0.9. So this is 0.3, 0.4, 0.5, 0.6, 0.7, 0.8 and 1. Now if A1 can only be even, it can't be odd, therefore it can't be between 0.1 and 0.2, because then A1 would be an odd number. So this is forbidden, this region is forbidden, this is forbidden, this is forbidden, this is forbidden, and that is forbidden. Therefore A1 can only be in these intervals. Then you break up each of these into 10 parts, and the second decimal would again be in one of the 5 intervals out of the 10, every alternate one is permitted. And this process is self similar, at every stage it is exactly the same process. Therefore what is happening is that you have got a resolution, a demagnification factor epsilon, which is 1/10, and at each stage you are breaking up a unit of the previous stage into n of epsilon parts, where this is equal to 5, because the other 5 have been erased, and therefore d0 equal to log 5 divided by the log of 1 over epsilon, which is log 10. That is the fractal dimension. Okay. Now of course you could make this question a little more sophisticated by asking for various probabilities. If I did not associate equal probability measures with all these things, but I had biases to one side or the other, then I would get a multifractal, and I would get generalized dimensions dq which are different from d0. But otherwise once I do this kind of coarse graining and I continue this, then all the dq's are the same as d0, nothing changes, and it is just a regular fractal rather than a multifractal. Okay. And finally we come to the last question. Pardon me? A multifractal is something where, well, many ways of defining it, but if you have many dimensions, generalized dimensions associated with a set, I call it a multifractal. Okay. In other words, if you have a whole spectrum of dimensions dq as we defined it, generalized dimensions, then it is a multifractal, but if all the dq's collapse to some single value d naught, then it is just a fractal. So these are in that sense regular simple fractals. Okay, the next one was just a problem in matrix algebra, and it went, 3 identical tall glasses A, B, C contain water to respective heights x0, y0 and z0. The levels in A and B are first equalized by pouring water from A to B or B to A depending on which one has more. The levels in B and C are then similarly equalized, and then C and A are equalized. So that is a complete operation, and then you repeat this operation over and over again, and it is intuitively clear that eventually the levels in all the 3 would become equal. If no water is spilt, then that level would be 1/3 of x0 plus y0 plus z0. But the question is, what is the rate at which this limit is approached? In other words, what is the actual value, what are the values of the levels in the 3 classes after n iterations of this step? So this is done in a very straightforward way. We could randomize this problem as well, but this is completely deterministic. So it is just a set of 3 recursion relations. I start with some 3 glasses which are, and this one has some x0, this one has maybe more, we do not care, y0, and that one has some z0, and you keep pouring from one to the other and you ask what happens to the levels finally. Well, we start with x0 and let us put them down as a matrix y0 z0, and I take the 2 glasses A, B and equalize. So what I have done is to make this x0 plus y0 over 2, x0 plus y0 over 2 and z0, and then I do the same for B and C. So this remains as it is, but these 2 guys get equalized. So this is this plus that divided by 4, so it is x0 plus y0 plus twice z0 divided by 4, and so is this. In this fashion, and then I change C and A, I equalize these 2 levels, which is equivalent to saying I take this and take the arithmetic average of the 2, which is a 2x0 plus an x0, so that is 3x0 plus a 2y0 plus a y0, that is 3y0 plus a 2z0, and the whole thing is divided, this is the common denominator already, so it is equalized, made into 8 out there, and that is exactly what you have here, 3x0 plus 3y0 plus 2z0 divided by 8, and this remains as it is. Divided by 4. So what has essentially happened is that you have a column vector x which is x, y, z in this fashion, and what we are doing is to say x at time n plus 1 is equal to some matrix, let me call this matrix T, x at time xn, and the matrix T is written down there. It is equal to 3/8, 3/8 and 1/4. On this side it is a quarter and a half, and again it is 3/8, 3/8 and 1/4. That is it. And this of course would imply that x at n is t to the power n, x at time 0. And we need to find this. We essentially need to take the nth power of this matrix. Now what is interesting is to find what its limit is going to be, we are guaranteed that what will survive finally for x, y, z would be 1/3 of x naught plus y naught plus z naught, all the 3 would become equal in this case. So the system would tend to the uniform distribution, all 3 glasses have exactly the same amount of liquid. Now what is noticeable about this matrix? It has 0 determinant, but it is a stochastic matrix because the material is not being lost. So in some sense it is basically a stochastic matrix, in the sense that the sum of the rows is equal to 1, each row sums up to 1, each column also sums up to 1, it is doubly stochastic in this case. Is it a symmetric matrix? Not as it stands, not as it stands. So we really can't immediately assert that the left and right eigenvectors are the same, can't assert that at all. Notice that because the rows add up to 1, you end up with the uniform eigenvector. So 1 1 1 is an eigenvector, and similarly 1 1 1, a row vector, is also an eigenvector, a left eigenvector of this. What are the eigenvalues of this matrix? Yeah, 0 has to be 1 because the determinant is 0. 1 would be an eigenvalue, exactly, 1 would be an eigenvalue, that is what would correspond to the equilibrium distribution finally. So eigenvalues lambda 1 equal to 0, lambda 2 equal to something, and lambda 3 equal to 1 plus 1, 1 would be an eigenvalue. The third one, in this case not hard to discover, it is minus 1/8. So now we can diagonalize this matrix, write down what the t to the power n is and so on. 0 would just goes remain 0 and the 1 would remain 1, but then when you take the nth power, this guy would give you minus 1/8 to the power n. That gives you a time scale in the problem. I am not going to work that out, it is a matter of detail, but we can see that eventually x will tend, as n tends to infinity, xn, this would tend to x naught plus y naught plus z naught over 3 1 1 1, normalized to this. And the question is, what is the time scale? How does it do so? What is the characteristic time? So you have an exponential here, and if you raise lambda 2 to the power n, you have 1/8 to the power n, which could be written as e to the minus n log 8. So this would imply that there is terms of the form e to the minus n log 8 here. So a characteristic time tau would be like log 8 inverse. That is the interesting part. So it is a deterministic process, it is a map, but it is very much like a Markov chain in this case. It is given by a certain transition matrix, and this thing here is a stochastic matrix, so it is exactly like the transition matrix for a Markov chain, and it has an equilibrium distribution finally. As I said, we can make this problem more interesting by putting in random elements into this, some probabilities with which you do certain operations before others and so on, and then the matter would become a little more intricate and interesting. But this is completely deterministic, you equalize A and B first, B and C next, C and A third, but you can do this in various orders with various probabilities, and then you could ask similar questions. What is the probability of finding the distribution of the levels at a certain stage? This is also answerable. Okay. So I am more or less done. And, okay, I would like to sort of conclude. Anything else? Any other questions on all that we have done so far? I have to, yeah, the question is what is meant by a correlation function, an autocorrelation function for example, the simplest of these cases. So let me explain that in brief. Again let me take the example of a random variable x, a scalar random variable, and ask what can you say about this random variable. It does not have to be a Markov process, it could be anything at all. Then clearly the following are relevant questions to ask, to relevant physical quantities to analyze for a random process. One of them would be to say, if you have this, what is the average value at any instant of time. Okay. It does not have to be a stationary random process. If it is, then the average is independent of time, because you would evaluate this over a distribution which is independent of time. You can generalize this and ask what is the nth moment of this object. This too, if it is stationary, would be independent of time. Now you could have stationarity at the level of the mean, at the level of the autocorrelation and so on and so forth, but let us assume we take the definition of a stationary process in the strict sense of the word, namely all the distributions, all the joint probability distributions, the single time ones are independent of time, the two time distributions depend only on the time difference and so on. In other words, the origin of time is irrelevant. The next question you could ask is, alright, what is the average value of the product of the value of the variable at some time t1 and the same variable at a later time t2, what is this equal to? This would in some sense characterize the amount of memory present in this variable, in this random variable. If it is a delta function in t1 minus t2, then I would say it has no memory whatsoever, like a noise, a white noise for instance. But in physical problems this would always depend on t1 and t2. If the variable is a stationary random variable, then I would expect that this quantity would become actually a function only of the time difference between t1 and t2 and not of the two absolute times t1 and t2 separately. In fact, I should be a little more careful here. I should really define x of t1 minus the average value at that time, x at time t2 minus the average value at that time, and then take the average value of this, and this is what I would call the correlation function, which in general is a function of t1 and t2. This is what I would call the autocorrelation function of this random variable. If this is a stationary random variable, then certain simplifications occur. So stationarity implies immediately that this thing becomes the average value of x at time t1 minus the average value at x, average value of x, and that is independent of t. So it is just this average. But we can separate this out, it is x at t1 times x at t2 average minus average of x times average of x here minus another of those same things, because these quantities no longer get averaged because they are constants, and then plus the average of x the whole squared. So you could also write this as C of t1 t2 to be equal to x at time t1 x at time t2 minus x average the whole squared. So it is like the generalization of the variance, except that you have time arguments here. And now the statement is, if this is a stationary random variable, what is meant by this thing here? Let us try to write it out. Suppose it is a continuous variable, let us try to write out what we mean by this explicitly. It is an integral over all values. Let me call x1 the value at time t1 and x2 to denote the value of the variable at time t2. So it is an integral over all x1, it is an integral over all x2, and then x1 x2, because that is what you are averaging. this product is what you are averaging, multiplied by the joint probability density that you have x1 at time t1 and x2 at time t2. Okay. But this quantity by definition can also be written, so this quantity is equal to that, let us forget this for the moment. So apart from that, this thing is equal to this, and then this is equal to integral dx1 integral dx2 x1 x2. This joint probability, if for instance t2 is greater than t1, t1 is the earlier time, I use slightly different notation, I use the later times I move to the left, so let me leave that same notation, let me write this as x2 t2 x1 t1. Pardon me? Yeah, I can shift the origin, but let us do it slowly. So this is x2 t2 given x1 at time t1 multiplied by p of x1 t1. This is the single time probability, this is the two time probability densities in this case. But since it is a stationary random variable, we have assumed that this is independent of t, it is just this quantity here, and then once again since it is stationary I write this as t2 minus t1, and I could write this as 0, but let us just remove that altogether, it stands for some origin of time. So we come to the conclusion that C is in fact a function of t1 minus t2 in this fashion. So this thing here is a function of t1 minus t2 to start with. Let us forget about this, I mean let us set that equal to 0 or shift the whole origin of this variable so that the mean is 0. But you can say a little more than that. Notice that if it is stationary, you could actually write this C of t1 and t2, so this quantity x of t1 x of t2, if I subtract from both sides t1 and I set t1 equal to 0 or I shift the origin to t1, you could also write this as x at 0 x of t2 minus t1. But I could also have shifted t2, right. So you could also write this as x of t1 minus t2 x of 0. But if these are classical variables, there is no problem about commuting them. So this is also equal to x of 0 x of t1 minus t2. So in fact it says that this correlation function is a symmetric function of the time difference, the two time arguments. So you actually come to the conclusion that C of t1 t2 is equal to C of the modulus of t1 minus t2. It is a function of the magnitude of the time difference, and it gives you some idea of how rapidly the system loses memory. In the case of a dichotomous Markov process, this was a single exponential, but it does not have to be so, it could be much more complicated than that. But what we do know is that you end up with something which is a function of this modulus alone. Now physically I would expect, if the average value were 0 for example, I would expect the behavior of the C, so let us call it C of t as a function of t, and let me just plot the positive side of it, the negative side would be symmetric in this case. It would start here and perhaps go to 0, it would decay, maybe exponentially, maybe slowly like a power law, but the memory would gradually go down. Now that would be decided by how fast the limit of this quantity as t2 minus t1 goes to infinity goes to p1, because I know that in the limit this forgets the initial condition, and the limit of this quantity is in fact just P1 of x2. So it would depend on that, it does not have to do this, it could do this, it could do crazy things. Physically I would expect it to be a non-increasing function, I would not expect the correlation to increase, but of course it could be purely periodic. Suppose this variable is not a random variable at all, but it is the position of a simple harmonic oscillator and I take averages over time, what would you expect this correlation to be? Suppose it is a simple harmonic oscillator of frequency omega, what would I expect this correlation function to be? I now average, there is no averaging, I average over the actual dynamics, I know if I start with an x0 I know what the system does. It would just be a periodic function once again, it will not go down at all, it will just start at unity and then perhaps do this. But in real random variables, more realistic situations, I would expect this correlation to die out, and it is a measure of how much memory there is in the system. In fact you can find a time scale from this C of t, because notice that you could integrate this C of t. So I could do the following. In the case of a stationary variable, I could take C of t, I could take the quantity x of 0, x of t, divide by x squared so as to make it dimensionless, and integrate this over t from 0 to infinity, and I call this the effective correlation time, because it has physical dimensions of a time. As you can see, if this is mean value of x squared e to the minus lambda t and I do this integral, then the correlation time is just 1 over lambda for a single exponential, but otherwise I get some effective correlation time. There is another thing you do with the correlation function, and that is the following. You could also take its Fourier transform. So you could also take, well, let me call C of t the correlation function, you could also take integral minus infinity to infinity dt e to the power I omega t C of t, and that is a function of omega here. So you could ask what is this equal to, you could call it something else, so let me call it S to show that it is over the function x for the random variable x. Let me define it in this fashion here, and this is called the power spectrum the power spectral density, or for short, or power spectrum of the random variable x. If x is a noise, then this thing here tells you in rough terms the intensity or the strength of this noise in a frequency window between omega and omega plus d omega. And if it is white noise, this is a delta function and then it goes to a constant. So that is the reason why you call it white noise, because the power spectrum is flat. Physically that will never happen, of course, we know that things will always go down. So the power spectrum, if you plot this S of omega versus omega, in the ideal case for white noise it would look like this, ideal white noise, but in practice it would come down in this fashion. And a great deal of information is obtained by looking at the power spectrum. So you could in fact start with any time series for any random variable, even a chaotic time series, and look at the power spectrum. If the system has hidden periodicities in it, then they will be detected here. So anything that becomes periodic here, you notice if I have a single period here of period omega 0, what would this become? It would give me a pulse, it would give me a delta function at omega naught. So what happens in practice is that you have a power spectrum which looks like this, maybe there are some spikes of this kind, and at those spikes you know that there are periodicities in the system. So in a complicated time series, the power spectrum, which is a Fourier transform of the autocorrelation function, helps you to detect hidden periodicities. If the system is completely noisy, white noise, it will have absolutely no such structure at all. Even the way it falls off tells you something about the underlying random process, whether it goes like a 1 over f squared or a 1 over f or whatever, where f is a frequency. There is a whole class of processes called 1 over f noise, which corresponds to a power spectrum which dies down for large omega like 1 over omega to a power which is roughly between say 0.8 and 1.2, and this is called 1 over f noise. It is very ubiquitous, it appears everywhere. If this were purely Brownian, a Brownian motion kind of noise, then it would go like 1 over omega squared. So the asymptotic fall off of s of omega also gives you physical information. If it is a chaotic power series as opposed to pure noise, true randomness or noise, then the power spectrum behaves very differently and it is very broadband. There are no periodicities, so it is sort of spread out, very irregular, very broadband. Whereas if it is complete noise, be like white noise or falls off like a 1 over omega to some power, and if it is periodic, then it ends up with spikes. If it is quasi periodic, it ends up with a large number of spikes. So the power spectrum is a physical way, a very practical way of seeing something about the underlying dynamics, regardless of whether it is deterministic or noisy or chaotic or a mixture of all these. Okay, shall we stop?